Hello, welcome to this AQA Further Math Statistics video in the series Discrete Random Variables 3. And in this first video we'll just do a quick recap of the binomial distribution that you should have met during your A-level math studies. So first of all, the notation we would use would be capital X is our random variable that will be normally distributed. So follows our binomial distribution indicated by what's in blue there. And the two parameters, the two quantities that define a binomial distribution are n, the number of trials, and p, the probability of success at each trial. And you should recall the conditions for a binomial distribution to be used as a suitable model. Each trial must be able to have only two possible outcomes, and we call those success or failure because one must be the opposite event to the other. The number of trials involved, n, must be fixed. The probability of success, p, must be constant for each trial, and the trials must be independent of each other. So this is a quick summary of the conditions that need to be able to be assumed or be known so that the binomial distribution can model a situation. And it's worthwhile making sure you're very familiar with those four conditions. So if we just have a quick look here, rolling a fair die 4 times, so you can end up getting a bit confused about what the parameters are. If we're doing something 4 times, we have 4 trials. We are interested in terms of our success event to get the number 5. So the probability of obtaining a 5 would be 1/6. And so the probability of a failure would be the opposite of that, and that would be 5/6. So here we only have two outcomes we're considering. That is getting a 5 or not getting a 5 when we roll the die. We have a fixed n, yes, n is 4. We have a constant p because p, the probability of obtaining a 5, will always be 1/6. And those trials are going to be independent. The outcome of one roll of a die is not going to affect the outcome of subsequent rolls. And so yes, we can use a binomial distribution to model the number of 5s that we obtain. So if we have a look here at the probability distribution function for a binomial, you can see the probability that our random variable takes the value r when we have n fixed trials and p probability of success is NCR or NR, written like this, the number of ways we can obtain r successes out of n trials, multiplied by p to the r, so the probability of r successes, multiplied by 1 minus p to the n minus r. The rest of the time we must have a failure. And remember, NR, written like this or like this, is the number of ways of choosing R items from n. So looking at this model again, where we can use the binomial, we have 4 trials. The probability of its success is 1/6, and we need to work out the probability that the number of 5s obtained is 3. And actually for this it's quite simple just to write down a list of the different ways in which we can, out of 4 rolls, obtain 3 5s. So the dash represents no 5. So you can see there are 4 different ways, and a 4C3 on your calculator actually does equal 4. So we're going to do the number of different ways, 4C3, which is 4 different ways that we can obtain exactly 3 5s in our 4 rolls. multiplied by getting a 5 and a 5 and a 5, so that would be 1/6 cubed, and then another outcome, and that would have probability 5/6. So there are several ways that NCR can be calculated. You could do it from Pascal's triangle, like this. But obviously that becomes pretty impossible if n is a large number. You can find, normally under the probability option, NCR on your calculator, or you can use this formula here using factorial, and hopefully you remember that n factorial is n multiplied by n minus 1 all the way down to 1. So if we just look at using a calculator here or looking at GeoGebra, and I'll put some screenshots up from GeoGebra in a minute. If we look at using the probability distribution function on your calculator, and here we're going to be using binomial PD because we want an exact value, we want x to equal exactly 3. We just need to give our calculator the variable information here. So we want the probability x is 3, our number of trials is 4, and the probability of success is 1/6. And you can just put that directly in the calculator, and the answer can be obtained very easily. So if you remember, we showed that it can be obtained by using the formula this way, and you can check that that will give you the answer obtained by doing it directly on the calculator, and that's quite acceptable and expected in the exam. So if we have a look at an example with a few more problems here, we want fewer than 4 heads, exactly 5 and more than 3, and it's a very good idea just to first of all sort out your model and then perhaps do a number line so that you don't make a mistake about exactly what you're being asked to find. So if we look at our model, clearly n is 8 because we're throwing a biased coin 8 times, and we are interested in the probability of obtaining a certain number of heads, and the probability of obtaining a head at any one trial is 0.3, so the probability of not obtaining a head would be 0.7. And the first part of this example is asking us to find the probability of getting fewer than 4 heads. So if we think about all the outcomes possible, fewer than 4 heads is the probability of getting less than or equal to 3. So it's just a good idea to spend a moment making sure you're getting that right. The second part of the question is asking us for the probability of getting exactly 5 heads, and the third part of the question, again, just think about your number line, and this time we've been asked to find the probability of getting more than 3. So that's going to be the probability of getting 4 or more, and that will be the probability, in fact, that x is between 4 and 8. So we have our random variable, and we know we can model it by a binomial distribution with n is 8 and p is 0.3. And it's worthwhile writing down this sentence before you start doing any sort of question. So if we have a look at the first problem, fewer than 4, and as we said, that's less than or equal to 3, and this is just showing you, you can have a look here at the shape of the distribution. You can see the probabilities at the extreme ends here get very, very small, so you can see the shape. Obviously we have a positive skew here because p is only equal to 0.3. And you can do that directly on GeoGebra using the probability distribution function, and we get the answer to 3 significant figures, 0.806. If we look at, this is an example here, using the formula and on GeoGebra, we want the probability of getting exactly 5 heads, so we want x to be between 5 and 5. We're only interested in 5. Or if we use the formula, we can do our number of different ways of choosing 5 from 8, HC5, multiplied by p to the 5 successes, 0.7 to the 3, the rest of them are failures. And either from GeoGebra or from your calculator, 0.0467. And finally here we want more than 3 heads. So as we said, more than 3 is the probability of getting 4 or greater, and because n is 8, the maximum number possible is 8, so we want to work out the probability that x lies between 4 and 8, not 3 and 8, but 4 and 8, remember. And either on GeoGebra or using your calculator, and this time using the BCD option because we want cumulative probabilities. We want the probability of being between 4 and 8 when n is 8 and p is 0.3. And so we obtain the answer 0.194. And that concludes this first video in this series.